Okay, so this is section 3.5. I know there's a typo there. But we're talking about angles of a triangle. How many degrees are there in a triangle? If we add up the three angles on the inside.
180.
Why?
Because.
All right, so today.
You could have 270.
No, you can't. So today, we are going to talk about why there's 180. You've been taught that. You've been told that. Now, after today, you'll have knowledge of why. Okay? So there's two theorems that are important to us. I guess they're postulates that kind of hopefully make sense to us. If I take any point that is not on a line. So let's say that I've got that line right there. So we call that our given line because it's provided to us, right? Okay. And I choose a point that is not on that line. So let's say that point right there. It's not on that line. That point could be anywhere. Okay. It could be above the line. It could be below the line, just as long as it meets the condition of not being on the line. Does it make sense? Okay. How many other lines will go through that point and be parallel to the given line?
0. Wait, 1.
Just one. Okay. So here are a bunch of lines that go through that point, right?
Yeah.
But as you see, I mean, they're all, I can't see this one touching the other line, but eventually they're going to touch, right? Okay. So all of these lines, so I can create essentially, you kind of see it mapping out like a circle or a, kind of it's like a fan blade or something like that. All those potential lines, right? But there's only going to be how many that are parallel to the given one? Just one. Okay. Maybe it's that one. Okay. And that's a postulate that we have to take for granted. We can't prove it, but we're going to make that argument that there is only one line that is not, that goes through a point that is not on the given line, that is parallel to the given line. That's what that phrase right there is saying. Does that make sense? How many lines would go through that point and be perpendicular to the given line? This one's a little bit easier to actually demonstrate.
1.
It's going to be 1. Okay, so if I look at what do we need for them to be parallel? We need 90 degrees. Okay, so if I look at that angle right there, it's 28.648 degrees, right? So we're asking how many lines go through that point C but are perpendicular to the given line. So if I choose maybe one of these lines, what's happening to that angle now? It's getting bigger, okay? And eventually it's going to get to 90. And now as it gets to 90, and I'll make it easier, we'll change the rounding here to 1 decimal place. As it gets to 90, what's it continue to do after 90? It's bigger and bigger, right? Okay. Now, the idea is we've got supplementary angles here, right? We got that angle, which is 154.5, but we got this angle right here, correct? Okay, which is going to be the supplement of that, which would be about, what we got, 0.5, so 55, 5.5, so 25.5 would be that angle right there. Okay, if we go back to where it was 90, we'll cheat even more. Okay, so if it's 90, that means this angle right here is 90 and that one is 90, right? But so that means they're perpendicular, but nowhere else will they both be 90, right? They're always going to be, one's going to be bigger than 90 and the other one's going to be less than 90. Does that make sense to everybody? Okay? So when we have a given line, like this black line, and a point that is not on it, there is always one line and only one line that goes through that point and it's parallel to the given line. And there's one and only one line that goes through that point and is perpendicular to the given line. Okay? So that's a key fact for us. And the parallel postulate is actually going to be what allows us to prove this theorem here. It's called the triangle angle sum theorem. Triangle angle sum theorem. And it simply states what you've known since, I don't know, 4th or 5th grade. Okay, there's 180 degrees inside that triangle. Okay, we add up all three angles, A, B, and C. They're going to sum every single time to 180. Does that mean that angle A, B, and C are supplementary? Why not? Well, they don't. I think you're trying to say that they're together, they're adjacent. Supplementary just means two angles. Okay. They don't necessarily have to be adjacent to be supplementary, but they do have to have two. They have to be two angles, and this would be three. Okay. In order to prove, so we're going to prove this. In order to prove it, we need. We're going to use a definition of something that we haven't talked about before. It's called an auxiliary line. Okay. What does auxiliary mean?
Power.
Okay. So what are you thinking about when you say power?
Like a auxiliary.
You're thinking about your aux cord, right? Okay, on your phone or your radio or your car. But that's not really referring to power. But that's where most people think about auxiliary. Okay. Has anybody ever been to Lima Senior in their gymnasium?
Yeah.
Have you ever been, like, if you go like underneath the flag in their gymnasium, which is on the, I believe, the east wall or the west wall, you go out the door. Maybe it's underneath the scoreboard. You go out the door. There's another gymnasium. Did you guys know that? They have another gym. There's no seats and there's no bleachers, and it's just basically a gym that goes like wall to wall, just gym floor, basketball courts. Okay? It's called an auxiliary gym. What do you think the word auxiliary means in that situation?
Extra.
Extra. Okay? So when I say auxiliary port or auxiliary cord, it's an extra thing. Okay? It's a, because obviously you use, a lot of those things that have aux cords use Bluetooth, right? So the Bluetooth is the primary source, and then the aux or auxiliary is the secondary source or the extra source. So anytime you see the word auxiliary, it's referring to extra. Okay. So in this case, an auxiliary line is a line that we add to a diagram that is extra, but we know it exists. Okay. And usually when we're going to use an auxiliary line in our proofs, what we could do is, in any one of our proofs that we've done so far, we could have added an extra line. Because all we need is 2 points, right? Okay. But usually when we use an auxiliary line, I don't want to say usually, I want to say always, when we use an auxiliary line, there's going to be a purpose for it. Okay. A lot of times it's hard to decide when to use an auxiliary line or when it's necessary. So in this class, at least the first 2 or 3 times that we need it, I will present it to us. We'll have this discussion. This is auxiliary line. This is why we need it, that kind of thing. But if I start with this triangle right here, okay? If I start with that triangle, just kind of visualize this for me based off of what we just talked about. If I take AC and I let AC be my given line, and I just quickly kind of hide that segment and hide that segment, and I have this point B now. Is point B a point that is not on the given line? Does that make sense? How many lines go through B that are parallel to this given line? Just one, right? Okay. And that one is this line right here that we're going to add to our picture. Okay. It's the auxiliary line. Does that make sense? But we've added it so that it has a particular useful feature to us. we know that this auxiliary line is parallel to this line AC. Does that make sense? Okay. Now, we could have done this anywhere. Okay. Usually you see this proof done with the auxiliary, I had trouble saying that word. Auxiliary, auxiliary line, right there. We could have added it right through here as well. Would you guys agree that there's a line that goes through A that would be parallel to BC?
Yeah.
Or we could have added it over here through C so that it's parallel to AB. Either one of those three is an option. We just usually use that top one, okay? So why does that help us, okay? So we're gonna create this proof, and what I'm going to do is we're gonna do this whole proof without the notes, so do it from scratch. We'll come to the side. This might not match 100, so if you're using this one in your notes, this might not match 100%, which is fine. I don't like the way that they set this up in the notes that I've used. I would at least rewrite the statements in the, you don't have to redraw the picture and all that kind of stuff, but. All right, so here's the kind of structure of working inside this proof. Remember, your given information and your prove information for a theorem are the if and then parts respectively, okay? Meaning, I have to take if I want to try to prove this theorem that there's 180 degrees in my triangle, then I need this part here to be my if, and I need this part to be the then inside this statement. Now, this statement is one of many statements throughout the course that is a theorem, but not written as an if-then statement. But it can be. Everything that we see in this class and mathematics can be written as an if-then statement. So I'm going to rewrite this and say, if the shape is a triangle, then the sum of its angles is 180. My hope is that you can see that says exactly what the theorem in yellow says, okay, or in that yellow box, okay? If the shape is a triangle, then the sum of its angles is 180. It says the same thing as the sum of the measures of the triangle, or the angles of a triangle is 180. Okay, so why do I do that? Is because I want to know, what do I start with? What is my if statement? I just got a triangle, a shape that's a triangle, right? So that's my given. All right, now I want a specific triangle so I can talk about it, so I just call it ABC. And when we talk about triangles, basically the rest of this course from here on out is mainly talking about triangles. So we're going to see this notation a lot. They put the little triangle out front, and then they use the three vertices to name it. So we read this triangle ABC. All right, so we start with that, then prove this part. The sum of its angles is 180. Well, is one of its angles angle A? Is one of its angles angle 2? And is one of its angles angle C? Are we showing that we are summing them to a total of 180? Okay, so we have taken the if and then parts and we have put them together here and written them in a specific way so that we can actually talk about specific objects throughout our proof. Okay, it would be really hard, instead of saying like angle A, to every time I want to reference angle A, I say it's the angle that's on the bottom left of the triangle in my picture. Because that would be really inconvenient to write, correct? Okay, so that's why we do those things. Now what we're going to do is we're going to write our first statement, which is that we are just given triangle ABC. Okay, so this next one, and this is where if we ever need this in a proof, I will provide this for you. But it says construct or draw, and we'll talk about the difference in those things later on in this chapter a little bit. But construct or draw the line PR so that it is parallel to AC. Okay? Now we know we're allowed to do that because I'm going to write two things here. Definition of an auxiliary line. Okay? And because I know that line exists. I know it exists. I'm allowed to do it. I'm allowed to add an extra line to my picture. Okay? But I've added it in a way so it was parallel to AC. We had that line, that postulate said there exists exactly one line through a point not on a given line that is parallel to the given line. I know that's a lot to say, and we can condense that later on, but the first time that we see this, I'd like to write the whole thing out. It's called the parallel line postulate. We talked about the first one we talked about in these notes. But it says there exists through a point that is not on my given line. So I'm assuming that AC is my given line, and B is a point that is not on it. Then there exists one line that passes through B that would be parallel to AC. Does that make sense? Okay, so that's so what we're saying right there is exactly what I was trying to show and demonstrate right here when I deleted some of those segments and shown that, okay, if I got this B, that's not on this line, there's one parallel line that goes through there, okay? So like I said, that was, you can condense that whole phrase with the parallel postulate or parallel line postulate. So we've got that, okay? So now, if I were to give you this on a quiz or a test, those two things would be filled in for you. Those are, I think, especially the first time, obviously, difficult to know that those are necessary. Okay? So now what I want to do is run through our structure for completing a proof. First thing we do is we look at our given and see if there's any vocabulary. Okay, and there is vocabulary. Triangle is a vocabulary word. Okay, but it's basically a vocabulary word that creates the shape. Okay, it's like a creation type term. Okay, so it just tells you what a triangle looks like. Okay, it's three non-collinear points connected with segments. Okay, that's what definition of a triangle. So, or a three-sided figure if you want to get down to like the most basic phrase. That doesn't really lead me to anything new. Okay, anything useful. So we're not going to use that. So we're going to skip that, and we're going to go look at step 2. Is there any vocabulary words that kind of jump off the page to you in statement number 2 that we introduced? So careful. I know where you're going, or I think I know where you're going with that eventually. But if I look at that phrase right there, is there a vocabulary word in there that would be useful to us? Maybe not written out as a word, but used as a symbol? Parallel. Okay? If I've got parallel, so I've got this segment up here, parallel to that segment, right? Okay? So let's see what that tells us. If I look at, so just focusing on my parallel line, so I'll help by removing maybe this line right now. And maybe extend this one a little bit. Extend that one a little bit. Okay, based on the angles that we have here, the angles that are in the triangle, and maybe these angles up here of 1, 2, and 3, is there any relationships that you can argue? And that's the angle that's in the triangle, right? What are you going to say about those two angles there that I just highlighted? They're congruent, right? They're alternate interior angles. So let's say angle, so that was angle A and angle 1, right? So let's say angle A is congruent to angle 1. I'm just going to say alternate interior angles theorem, which said if two parallel lines are intersected by a transversal, then alternate interior angles are congruent. Okay, so that's nice, right? Angle A, that's something that we didn't necessarily know at the onset of the problem, so that's new information. I'm going to put markings in those. What about looking at maybe that line there, and now that transversal? What angles, very similar to what we just talked about, what angles there would be congruent if I got rid of that one? Angle 3 would be congruent to what? Angle C, right? Does that make sense, everybody? Okay, so we'll write that down. Now, are 3 and C, are they still alternate interior? Okay, so I'm going to put that underneath the same. So angle C is congruent to angle 3. And it's the same reason, so it's all put under the same statement. Now, I'm going to put 2 marks in there because I don't know, they might be, in some cases they are, but I don't know if angle A and angle C are congruent. Does that make sense? Okay, so I don't want to put just 1 mark in C. I want to put 2. Okay, is that all right with everybody? All right, so now let's go through and do this. Let's say that if I say, and we could do this with either one of these angles, and this might be something that doesn't make initially a whole lot of sense to you, but it will eventually. If I say the measure of angle PBC, so let's look at that angle there, PBC. Like I said, you could have done PBC or we could have done RBA. But if I look at PBC, it's that angle right there, right? Make sense, everybody? What 2 smaller angles makes up PBC? 1 and 2. So I'm going to write the measure of angle PBC is the same as measure of angle 1 plus the measure of angle 2. Now the reason for that would have been that they were 2 angles that were adjacent. They share this ray right here. If I take 2 smaller angles and add them together, to get a bigger angle, isn't that angle addition? Does that make sense? So step 4 is angle addition postulate. Okay. In a moment, you'll see the purpose of doing that. But now, what can you tell me about that green angle that we've highlighted up here and that blue angle? They're supplementary. So step 5, I'm going to say, so that green angle was a measure of angle. Let's write it this way. Let's say that, just so everybody knows this, and this, I don't know if it wrote this in that, the way that I had it predefined, but if I say angle PBC and angle 3 are supplementary. Why do we know that they're supplementary? we form a line, right? Don't they form that line PR? So we have two angles that form a line. And we can say that they're supplementary. That's because they are a linear pair, right? Linear pair postulate. Now, step 6, we just introduced the word supplementary about those two angles. So let's write down what that means to us. It means the measure of angle PBC plus the measure of angle 3 equals 180, right? Would you guys agree with that? Okay. Definition of supplementary angles. Okay. Keep rolling with that for a moment. So right now I've got PBC plus 3 is 180. But have I anywhere throughout the proof already identified another way of identifying or talking about measure of angle PBC? Is the measure of angle PBC the same thing as 1 plus 2? So can I replace that? Can I take this 1 plus 2 and put it right here? So let's do that. So we got measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals 180. And all that is substitution, right? Okay. So I'll go back up to my picture real quick, and you can see basically all we've done. And then hopefully this makes sense. And some of you probably may want to jump to this right away, which would be, I wouldn't have had a huge argument with it. But it doesn't make sense if I look at my picture that 1 plus 2 plus 3 is equal to 180. Do those three add up to a linear structure, PR? Okay. So hopefully that makes sense. But now that doesn't help me in regards to talking about the triangle, right? But what did we say angle 1 was the same as? Same as angle A, wasn't it? Okay, so right here, we said A and 1 were the same thing. So A and 1 are the same thing. So what can I replace that with? Measure of angle A. Okay, measure of angle 2 is already inside my triangle, so I'm going to leave that one alone. So I'm going to just carry that straight down from line 7. Going back up here, look at my picture. Didn't we say 3 and C were the same thing? So right here where I see 3, I can replace that with measure of angle C. And all that is substitution. And what have we shown? Is A an interior angle? If I go back to just basic picture, A is that angle right there, right? Add to it angle 2, which is that angle right there. Add to it angle C, which is that angle right there. Are we adding all three angles up? And if we said that it should equal 180. Okay, so that's the why of our triangle having three angles that add up to 180 degrees. And now no matter, because we used A, B, C, 1, 2, and 3 as our angles, and we didn't use specific measurements, that is now consistent for every single triangle we ever draw. Okay? Every triangle we ever come in contact with, these three angles are going to add up to 180 degrees. Is that all right? Okay. That's maybe the best example so far in this course of us being able to take a fact and produce an explanation of why it's true. And that's one of the things I hope you guys get out of this course is not so much, can I in 5, 6, 7, 10 years when I leave high school, can I use the mathematics, the geometry that I learned in 9th or 10th grade math, which some of you will be able to, and I hope that some of us do. But my real hope is that you leave this course and you have become more interested in knowing why things are the way they are, more investigative, because that makes kind of more able to not just take somebody's word for granted and probe into the facts and make your own conclusions. Does that make sense to everybody? Okay, right now, I hear, and I don't know, I think when I was your age, I probably didn't pay much attention to the news and the politics and all that kind of stuff. But if you watch any of that, your parents watching that, you might be hearing a lot of stuff that, you know, when I was in school, I think, and even when your parents were probably in school, that you watched the news and like it was legit, like they were telling you facts. Okay, anymore, it's not. Okay, you can hear something on one broadcast, and they're saying that it's a fact, and then you go to a different broadcast and they're saying the complete opposite is a fact. So you have to be investigative. You have to do your own little research. Does that make sense? And hopefully that this course kind of gets you thinking along those lines. As we move through and talk about the rest of this information, this section, just a quick definition for triangle: figure formed by three segments joining three non-collinear points. The points have to be non-collinear. So if I just say it's a figure formed by three segments joining 3 points, well, if my points are like that, does that give me a triangle? So one of those points has to be moved away from the others. So maybe my keyboard is all messed up. It doesn't do what I want it to do. All right, so one of these points has to be moved away from the others. So they're on a different line. Now we would get a triangle, right? Okay, so we have to have that word non-collinear here. Sometimes you talk about a triangle, they'll talk about it, they'll say a triangle is a polygon with 3 sides, which is fine, but we haven't described what a polygon yet is in this class, right? Okay, so I'm going to use this vocabulary instead until we get to, I think it's section 5, or chapter 5 that we talk about polygons. Types of triangles. Okay, you guys know these things. And we can use kind of combinations of these words to classify things. So a scalene triangle is a triangle that has no sides congruent. Did you guys know that before? So scalene is no sides congruent. Isosceles means at least 2. So we're setting the floor. Okay, we're setting the minimum that we could have. So what's the maximum I could have that are congruent? 3, right? So 3 sides congruent would still be isosceles. 3 sides congruent would still be isosceles. But if all 3 sides are congruent, we like to better classify it as equilateral. But it is still isosceles when it's equilateral. Does that make sense?
So it's both then? Like if you're isosceles.
So an equilateral, and this is a good thing to write down. Equilateral is both isosceles and equilateral. But an isosceles triangle, we can't say whether it's both. Does that make sense? We don't know. Okay, because when I say isosceles is isosceles, bare minimum is that it's 2 sides are congruent. I'm not saying that I've got that third one yet. Does that make sense to everybody? It's like saying, like if I asked the question, so this is a common question I ask in test quizzes. If you have an isosceles triangle in front of you, and that's all you know about it, you don't have a ruler, you don't have any measurements, I just tell you that it's isosceles. So if that happens, can you tell me that it's equilateral? No, you don't know, right? You don't know enough information to say that it's equilateral. But if I tell you you have an equilateral triangle in front of you, can you tell me that that is isosceles? Yes, okay. It's the idea, is a square a rectangle, or is a rectangle a square? You've heard that phrase before, right? A square is a rectangle, but a rectangle is not a square, okay? Because there's added features to become a square, right? So there's added features, there's more criteria needed to become equilateral in regards to a triangle. Okay, there are other shapes are referred to as isosceles and equilateral. So isosceles in general, when we're talking about isosceles triangles, we're talking about 2 sides congruent. We're talking about equilateral triangles, we're talking about all 3 sides being congruent, okay? What's equa mean? What do you think that root word or prefix equa means? The same. I mean, it comes from equal, okay? What's lateral mean? Explain. If I'm playing football and I lateral the ball, behind, or the rule is if I lateral the ball, it can't go forward, right? So that means it allows the ball to go to my side or behind, right? So my side or back. So lateral means side. If I have good lateral movement, okay, you heard that in sports? That means I move side to side pretty well, okay? So lateral means sides, okay? Now you said line, so I was thinking like, so if I'm talking about like thinking about water lines that go into people's homes. So let's say that I've got a water, so let's say we've got like a street here. And we got water lines running parallel to the street, right? So if there's a house over here, okay, this line keeps going straight, but then there's they call that, so that's called a lateral that comes off of that water line, but it goes to the side. Does that make sense? So I didn't know if you meant like so it's a water line, that kind of thing, okay? But that's called a lateral. But lateral means to the side, okay? So equilateral means equal sides. Does that make sense? So that's kind of that, I talked about at the beginning of the year, we can pull apart, if we're not certain, if we can pull apart the prefixes and root words, it might give you an idea of what we're trying to talk about. We're going to talk about acute. Okay, acute triangles are triangles that have all three angles less than 90 degrees. Okay, if we have an obtuse triangle that has one angle bigger than 90. Okay, why can't I have two angles bigger than 90? What would be a measurement bigger than 90? 91. So if I have an angle that's, let's say, 90 and 91, what do those add up to? 181. Does that violate a rule of geometry? Yeah, okay. So you cannot have more than one right angle. You can't have more than one obtuse angle because then you'll blow up your triangle. Okay. Okay, so equiangular, what do you think equiangular means? Equal angles, right? So equiangular, all angles are congruent. Now, if it's a triangle, how many degrees does my triangle add up to? 180. If they're all the same, if they're equal, don't I take 180 divided by 3 to find out what one of them is? So 60. So an equiangular triangle is actually going to have 60-degree angles. Okay? So that's a nice fact that brings in a measurement that is a fact, but we never had to measure anything. We never had to get a protractor out. Okay? We never had to get any other tools out, any like rulers or tape measure or anything. We know that to be a fact when it's equiangular. All right. A fact here that is also useful is that now this is only for triangles. Okay, like I said, other shapes are equilateral and equiangular as well. Okay, but if it's a triangle, when it is equiangular, it is also equilateral. Those two things are paired together all the time. So I don't want that. So a triangle is equal. If it's equiangular, it's equilateral. If it's equilateral, it's also equiangular. Okay, so it's a two-way street there. Now, here's my question: are other shapes that way? What is a shape that has four sides that is equiangular and equilateral? A square. So if I look at a square, we've got that there. So all those sides are the same. All those angles are the same, right? What is a four-sided figure that is just equiangular but not equilateral? A rectangle. Okay, so not all shapes, okay, are equilateral and equiangular. Does that make sense? Or if it's equiangular, it doesn't imply that it always has to be equilateral. Or if it's equilateral, it also implies that it's equiangular. Does that make sense? Okay. Theorem, sum of the measures of angles of a triangle is 180. We've already talked about that. You don't necessarily need to write that down. Okay. The reason I wrote that down is because we have this new clustering of statements that we're going to talk about. We've got so far in our statements categories, we have definitions, we have postulates or axioms, we've had theorems, and now we're going to have corollaries, or sometimes they're referred to as lemmas, L-E-M-M-A. But essentially what they are statements that follow directly from a theorem. Okay? The way I like to think about them is like the theorem is like the big brother or the parent, and the corollary is like the little brother or the little child. Does that make sense? Okay? They're used a lot, but they're generally pretty easy to prove. So what I'm going to jump straight down to this one here real quick. Okay? Just to show you how easy or how quickly they can be proven. We already figured out that there's 180 degrees in a triangle, right? Okay. Well, if I want to show that one where it says each angle of an equal angular triangle measures 60 degrees, that comes straight from that 180. If they're equal angular, that means I got 3 of them, right? 180 divided by 3 gets that 60 right away. See how that's a quick kind of connection, a quick line of thought to get to that 60? It's not an elongated proof, so we call that a corollary. Okay? I don't care, guys, as we go through, whether, and I said this before, I don't care if you remember things as postulates or if you remember as theorems or if you remember as corollaries. I don't care if you know that to be a corollary or a theorem. What I want you to know is that there's 60 degrees in every angle of an equal angular triangle. Does that make sense? I'm worried about the content and not so much what category of statement it belongs to. If 2 angles of one triangle are congruent to 2 angles of another triangle, the third angles are congruent. Okay? Sometimes this is, and I'll probably refer, because just the way that I was kind of trained with this stuff when I was in school, and we use this a lot, and I can't get this phrase out of my mind, what I'm talking about. It's called it's a corollary in our textbook, but you're going to hear me call it the third angles theorem. And the idea of that is this. Let's say I have 2 triangles. And I tell you that this angle is 100 and this angle is 100. Would that be 2 angles in those 2 triangles that are congruent? Okay, let me tell you that this angle here is 30 and this angle here is 30. Would that mean that you have another set of 2 angles in a triangle congruent? So let's say that's the if thing that is happening in front of you. That's the if hypothesis. It says if 2 angles of one triangle are congruent to 2 angles of another triangle. We've got that going on right here. Okay? So the reason this is sometimes called a corollary is because it stems from the 180 degree idea. How many degrees, if I look at just this triangle, how many degrees have to be left over for that angle? 50. How many degrees have to be left over for this triangle? 50, right? What's the connection then between that angle and that angle? They're the same, right? They're congruent. Are those the third angles of either of those triangles? So that's why we call it the third angles theorem. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are congruent. Okay? Hopefully that's not, we're not splitting atoms there. That's not an extremely difficult concept to see once you put those values in there. But it becomes something that we use a lot. Okay? So that's why it develops this kind of level of classification as a corollary. Okay? Or sometimes a theorem. You can't have more than one right angle or one obtuse angle. We've already talked about that. The acute angles of a right triangle are complementary. That should make sense as well. If I've got a right triangle here, okay, that's a right angle, right? So out of my 180 total, I've used 90. So what's that leave me with? 90 degrees to go to those 2, right? Now, I don't know. One might be 20 degrees and one might be 70, one might be 30 and 60, 45 and 45. I don't know what they are individually, but I know they are 2 angles who are going to sum to 90. So by definition, that makes them complementary, right? Okay. So those are some corollaries that eventually make some concepts easier for us. Okay. We'll stop there today. Okay. I'm going to open up a homework here in this section. You're not going to be able to finish all of it. You might be able to get a start on it, but there's some concepts here that we'll talk about tomorrow. Get through some examples, and hopefully tomorrow you'll have a little bit of time maybe to wrap up that assignment in class.